So the quiz is tomorrow. It concerns electric fields and charge. Excuse me.
Meaning like the formulas.
Right.
The
And-
first formulas.
You need to know the big idea, which is that force is charge times speed. That's a generally true statement. So if I have some electric field that looks crazy like this, and I place a charge in it, positive Q, like so, then that positive Q is going to experience a force that is in the direction of the field at that point, or is in the direction of the field at this point, or is tangential to the field. Negative charges are going to experience forces that are in the opposite direction of the field. As seen from the equation here, if I plug in a negative value, then I'll get something that is in the opposite direction of the field. You need to know that for single charges, the field generated by a single charge is going to be kq over r squared. It will have the magnitude of kq over r squared. But the direction, you're going to have to figure out by hand. You're going to have to figure it out using the fact that field comes out of positive charges and it goes into negative charges. So this equation gives us the magnitude of the field, but it does not give us the direction of the field. Yes.
I was going to ask some like the homework problem. So like when it says like you have an 84 Newton force downward, would be the charge of the field when you have like a negative electron in there, an electron.
Yeah.
And then it changes upward. So anytime you have a negative, you flip it. Like if it's east, it's now west.
Yeah,
Doesn't
basically
matter.
you're reversing your thought process for negative charges. So if I have an electron, and that electron is in some sort of electric field, and it experiences an 88 Newton force downward, then that indicates that the field is going to be pointing upwards at that point. Does that make sense? And you can tell that it should make sense because this field line has to come from a positive charge somewhere, right? And a negative electron should be attracted to that positive charge. So you can check your logic on that.
What if could you ever have an electric field from a negative?
When you have a negative charge, that negative charge is going to generate electric field that goes into it, not outward.
So then what would how do you know what your field is?
How do you know what your field is?
Like whether if it's a positive, like a field created by a positive.
I don't understand the question.
How do you know whether it's that one or that one in a problem?
Well, it'll give you charges and it'll give you a plus or a minus sign on the charges, usually.
Well, yeah, I mean, for the electron, you obviously know that it's 88 degrees or 88 Newton force downwards, but how do you know that the field isn't a negative?
Because the direction of the force on a negative charge is opposite to the direction of the field. That's what I was explaining here.
Yeah, but you can still have a
The field points in the direction of the force on a positive charge and in the opposite to the direction of the force on a negative charge.
in the direction of a negative charge. Sorry.
The field points in the direction of force on a positive charge, and it points in the opposite direction of force on a negative charge.
So just this with the squiggly lines of thing.
Right. So notice I've got electric field here, right? And so the field is pointing in this direction at this point. A positive charge will experience a force in that direction.
Does that mean the field is a positive field in a sense?
Vectors aren't positive or negative. Vectors have a direction.
Well, yeah, but I mean, is it the field emitted from a positive?
That means there's a positive charge back over here somewhere,
Okay.
and there's a negative charge out over here somewhere. Yep.
And it would be reversed if it was a negative.
Yep.
Yeah, but no, if the field was emitted from a negative, you know,
It
like,
would be emitted into a negative.
yeah.
Yep. That cleared up? What else do you need to be able to do? You need to be able to draw field lines. So if I give you a positive charge here and a negative charge here, let's make it definite. Maybe this is plus 2 microcoulombs, and maybe this is minus 3 microcoulombs, and I say now draw the field between them. Then you should be able to skillfully execute that. Why don't you give that a shot at this time?
Looks like that.
Yeah. Okay. So you should have field lines coming out or going in on this side? Out? And how many relative to this? 2 to 3 ratio, that's right. So if I have, for example, 4 of these right here, then I should have 6 over here. And field lines that come out of here are going to have a tendency to go into there, right? But of course, not all of them can. And so your field should look something like that.
Could you connect that one on the back?
And a really big loop around, yeah. Good. Any other questions?
So then in that case, the negative charge would be pulling the positive too.
That's right, and the positive will be pulling the negative to it. Both. So this guy is going to, because it's a positive charge, will be experiencing a force in that direction. And because this is a negative charge, it will be experiencing a force in that direction.
I like when we meet, they would be closer to the negative 3.
Yeah, it kind of depends on the masses, actually. So if this guy has a really small mass, maybe it's 3 electrons, whereas maybe this is 2 protons, then 3 electrons go, because their mass is only 1/1800th of a proton.
But they should be in the grade from that.
They'll actually have equal forces, so they'll meet in the equal forces. Right? Newton's third law, FAB equals FBA.
But one's plus 2 and one's plus.
The charges, not the force.
I thought the minus really would have more like charge.
No, they have to have equal forces. Because, take a look at the form for the force, Coulomb's law. Now switch the 2. Same force. Okay.
I need to switch.
There's symmetry in the equation. So if I compute the force of 2 on 3, it's the same value, same magnitude as the force of 3 on 2.
I already told you that's not the case.
No. As far as we know, Newton's third law is pretty absolute. Forces come in pairs, equal and opposite. What's the other things that you might need to be able to do? You might need to be able to deal with charge configurations where you have more than one charge. And you have to compute net force or net field as a result of those. And it's just a matter of adding the vectors by components.
Is net force the difference in net field?
No. Net force should be equal to charge times net field. Right? Force equals charge times field. But net force is usually done by adding up forces.
And then, but if they're like, with that number 13 in the triangle, though, you need to find like, you know, that crazy one, this one.
Yeah. So you have to find contributions from each and add up. And that's really it. I mean,
Is there anything with like the symmetry?
symmetry helps. It can cut down on your workload. It's a matter of being smart, being aware. That's really it. It's a lot less than you think it is. I think you're just overwhelmed because I'm not sure.
I just don't. Some learners don't really understand it.
Snow can be kind of like that.
Especially when you know you had a day and
So I want to review a little bit what we talked about with regard to electric potential.
Just keep on that one.
Yep. And in particular, I'd like to develop two formulas that we're going to use a whole lot. We started developing them yesterday. The first is if I have a single charge then the potential created by that single charge at a distance of r is going to be k times the charge creating it divided by r. And what's nice about this is that electric potential is a scalar and not a vector, so I don't have to worry about direction at all. Voltage doesn't have direction to it. It's either got positive or negative, and that's it. Positive charges create positive potential. Negative charges create negative potential.
What's negative potential?
Negative potential simply means below our arbitrarily chosen 0 point. So if I have an empty space that is clear of all charges, that's 0 volts. Well, no, not really. And the purpose of electric potential is so that we can measure energy, and in particular, just like force is charge times field, so also our change in potential energy equals charge times the change in potential. So if I have a 9-volt battery with a plus side and a minus side, like that, and I now place a coulomb of charge, which is a lot of charge, right here at the 9-volt thing, and I allow it to migrate over to the negative side, then it will lose 9 joules of potential energy in doing so. In other words, voltage or electric potential is the relative amount of energy per coulomb that is stored up. That 1 coulomb needs help. There.
how do batteries decay?
Batteries decay because the way the charge is stored in them is through chemicals. And those chemicals can either degrade over time or else they can leak over time. Basically, it's just electron transfer from atom to atom, right?
Is there a way to make a battery will not decay ever?
No, you could have really long decay times.
throw a freezer and like,
Interestingly, putting them in the freezer only adds a little bit of life to them. It doesn't do as much as you might think. There it is.
Why does the freezer actually have?
Well, it slows down reaction time. Big kinetics, reaction kinetics.
So then if you put it in absolute zero, it would last forever.
Yeah. Okay, now to get at this, let's do one more equation. Yep.
Actually, how cold is absolute zero?
273.
Negative 273.15 Kelvin.
Well, like, what would that be in
No,
Fahrenheit?
sorry, degrees Celsius. Sorry. Negative 273.15 degrees Celsius.
What would that be in Fahrenheit?
Negative 4, it's like 496 or something. There's a Rankine scale that uses Fahrenheit degrees and says 0 to the absolute 0. That's for what that's worth. Okay, so imagine that I have a positively charged plate and a negatively charged plate, and because of that, I've got constant electric field between these two. And what I'd like to figure out is, what is the change in potential as I go from point A to point B?
what if you just put like an electron inside and just like,
Yeah, that's exactly what we're going to do, except that instead of an electron, I'm going to put a proton. I'm going to put a positive charge right here at point A. And when I put a positive charge here at point A, does everybody agree that that positive charge is going to go this way? It's going to gain kinetic energy. Where is it going to get that kinetic energy from? From the loss of potential energy, right? So we can say that the work that is done, if these guys are separated by a distance d, the work that is done is equal to force times distance. Yes? And force is equal to charge times field, as always. Just like so. And the work that is done is equal to the amount of kinetic energy gained, which is equal to the amount of potential energy lost. And because of the way that we've defined electric potential, I can replace delta U with Q delta V. So that I get QED, the amount of work done, is equal to negative Q times delta V. And this gives us our very important equation for constant electric field. And that is that the change in potential is going to be the opposite of field times distance. So that as I go from plus to minus, my field points that way, and I'm going to go down in voltage. And I'm going to drop by an amount of field times the distance between the plates. Now, let's see how this actually works out with a couple of problems here. I'd like to take a look at number 4 on page 489. And in number 4, we have an electron requires 7.45 times 10 to the minus 16th joules of energy. Of kinetic energy. When it is accelerated by an electric field from plate A to plate B. So here's plate A, here's plate B, here's my electron, and it's going to be accelerated in this direction right here. And as a result, it gains the specified amount of kinetic energy. And now they want to know, what is the voltage difference between the plates? We'll call that delta V between the plates. And which one is at higher potential?
hypothetically, if both of those plates were negative
Mhm.
and you had the electron going to, would it just like find the middle?
If both of those plates are negative and same value, like negative 10, then there would be zero potential between them, and the electron would just freely drift. It wouldn't have a tendency to go one way or the other.
No, we're just like stay in the center.
No, it would be free to drift wherever. If one of them is at -9 and the other one's at -10, now there's a 1 volt difference between them, and the electron is going to go from the -10 to the -9. So it's all relative. It's not absolute in terms. Let's answer the second question first. Which one of these plates is the positive one, and which one is the negative one here?
Positive one.
B is the positive. Why is that?
Because of the negative electron charge.
Yeah, that's exactly right. You watch that negative electron is going towards the positive and away from the negative. So B is at the higher potential. Now the question is how much? And the only clue that we have is the amount of energy gained by that electron. And this is kinetic energy that is gained by that electron. So we can say that delta K for our electron is 7.45 times 10 to the minus 16th joules. Where did that kinetic energy come from? It came from potential energy. So what is the change in potential energy of this electron? Not quite. Close. Negative that. That's exactly right. Because my electron gained blah joules of kinetic energy, it lost blah joules of potential energy. And that's the insight for this problem. And we also know...
Is it negative because it's going from a negative, like, we need a push from the negative plate?
So 2 ways to answer that question. It's negative because it's getting a push from the negative plate, yeah. And it's negative because it has got to lose in potential whatever it gains in kinetic. Those two have to always add up to 0. They have to zero out. It's like accounting, right? Your credits and your debits always have to cancel out. So, we immediately have then delta U, the change in potential energy, is charge times change in potential. And we can plug in. What am I going to put in for the charge here? -1,
Coulomb. No, E.
-1 electron. What is the electron's charge?
1.602 times 10 to the negative 19?
Yep, that's it. Instead of the -19th coulombs. So that we get this for the phi equation. Now, this is easy to solve for delta V. Go ahead and do so.
My calculator. Batteries in my calculator.
And your iPhone?
Oh, yeah. What's the word? Disintegrated?
I think the word is didn't get replaced.
They broke open? Like,
No, I
started
don't think my
squirting out.
calculator was still
The rusty stuff.
I know it looked fluid covered.
Fluid powder. Oh yeah.
Acid.
No, it's just it's copper oxide.
So is that in my calculator's
Actually, it's probably fine. You just clean it out. A little bit of baking soda.
Yeah, because I have a
Christian, it looks like you've got it. What do you have?
Not technical, so.
No way.
that's what it's spitting out.
Yeah, well, it's not reasonable because
Yeah.
if I'm dividing 10 to the negative 16th by 10 to the negative 19th, I should get 10 to the third.
Yeah. Oh, that's right. I know exactly what I used.
And so wait, you put a negative in front of the electron?
Yes, because the electron has negative charge.
Charge.
Charge. What do you have? $465. That seems small. I would think it would be in the
Yeah,
thousands.
it's negative 650.
4650, yeah, that's right. But it's not negative, it's positive. Negative by a negative should be positive.
Yeah.
So is that a lot?
Oh, I did 100, not 0. Or, no.
No. Sorry, flash like you use 9.
Now, what does this mean?
Well,
Here's how we're going to picture it. We're always going to picture changes in potential as being like changes in elevation.
waterfall.
Like a waterfall, that's exactly right. And specifically, we're going to picture it like this. If we call the negative plate 0 volts arbitrarily, just we choose that, then this positive plate is going to be 4650 volts above that. Now, this is the major difference between gravity and electricity. Masses always go downhill, right? Positive charges always go downhill, but negative charges
Go up.
go uphill. So when I put my electron here, because it is a negative charge, shoop, it's going to go uphill and acquire kinetic energy as it goes. And that's the one weird thing about electricity in comparison to gravity.
But, so why does it go from the 0?
Well, because the 0 is lower than the 4650, and electrons go uphill.
Is that the negative plate then?
Yes,
And so the positive plate has 4,650 volts.
higher relative to the negative plate. It's all about relative differences here.
Well, what else would be affecting it? Relative.
Nothing. We get to choose arbitrarily where 0 is. So if I arbitrarily choose this to be 0, then this guy right here would be negative 4650.
What if you chose it to be 13?
Then this would be 4650 plus 13. See? It's just about relative differences. Now, here's an interesting thing. The problem did not tell us something that we didn't need to know. It did not tell us how far apart the plates are. Isn't that really interesting? The plates could be this far apart, or they could be this far apart, but we would still get the same potential difference, and the electron would still have the same kinetic energy. Now, how could that be? Well, let's examine the cases where we have near distance and far distance. If I spread the plates apart so that this is still 0 volts and this is still 4,650 volts, what changes is not the elevation between the two, but the slope between the two. Huh, that's interesting. I wonder what the slope is all about anyway. See, I'm a good calculus student, so I think to myself, I wonder what the slope is. So if I take a look at this slope, this is delta V, right? And this is the distance between the plates. This is delta V. And the distance, this is the distance between the plates. And the slope here is equal to delta V over distance. And so I go looking through my formulas to see if that means anything. And I see, oh yes, it does mean something. Delta V over distance is the opposite of the value of the electric field. Oh, interesting. So this means that the electric field is going to be the opposite of the slope of the voltage between the plates. In other words, if I push the plates closer together, what happens to that slope? It gets steeper, right? And as a result, the electric field gets stronger. And if I pull the plates far apart, then the slope gets less steep, flatter,
How does
and the electric field goes down.
well,
But the total change in voltage remains the same.
okay, but wouldn't it go faster if it was close together?
So, let's ask that question. When it's closer together, what happens to my electron? I let it go. And because the electric field is stronger, it accelerates more, right? But it accelerates over a shorter distance. So that by the time it strikes the plate on the other side, it has acquired exactly this amount of kinetic energy. If I pull the plates far apart,
Just gonna take a while.
it takes longer to get there, it accelerates less. By the time it gets there, same kinetic energy. That's pretty cool.
So what is it? Okay, I'm kind of confused with the negative field.
Why does the negative happen here? Well, you see how my slope is downhill, like so? But the field is actually going to point this way, like that. And the field is going to be, so my field is pointing this way from positive to negative, right? And so I ask, what is the value of the field? The value of the field is going to be positive in the direction of a decrease in voltage. So the negative sign accounts for the fact that field lines go from plus to minus and not the other way. Field lines go downhill, in other words.
So negative doesn't mean it just shows direction.
It's just showing direction, that's right. The field is pointing in the opposite of the direction of increasing voltage. Yes?
Okay, so this is kind of on a different thing. But, so if you have two magnets, like, in space, like with no gravity,
Yeah?
would they sort of attract, they would still attract, correct?
Yep.
Would they attract, like, further apart than you would,
No? No, they'd have the same attraction to each other. They just wouldn't have gravity pulling on them.
like,
So you would be able to place a magnet way here and down here, and you'd have a very, very, very slow attraction, assuming you put them north to south. Uh-huh.
even if you don't rotate?
So wait, if you put them like positive to positive and then like really try to be really close and then just let it
Well,
go.
north to south, yeah. So
Well, no,
magnets are not quite like charges.
Well, okay, then you put them south to south, really close, and then you just let them go and just really go.
Yeah.
Wait, so what if you had, like, two electromagnets that were, like, charged right next to and one started out as just, like, a positive, charge, you turn on the other one, like, as a positive?
Magnets don't have charges, that's what I was trying to say.
One is
Any magnet will always have both north and south on it. If you take that and cut it in two, then you create two magnets with north-south and north-south.
So what about an electromagnet? Would they, that's
Still
north
north
and
and
south?
south, yeah.
Did you ever have
It
one
would
with
just have
north-north?
north, it just have south.
Yeah, that's actually a famous result in physics. There are no magnetic monopoles,
That's a monopole.
single poles. There's
So-
no just a north pole or just a south pole.
Well, why not? Like, okay, so you know, like when you have like the train cars that like magnetically clip, and like sometimes like it won't clip on the actual thing, it like clips to the side of it.
Yeah. Because north and south are lined up that way?
Well, no, but like it's supposed to, but it doesn't. Like you can't
Yeah,
do
they're
it.
misaligned. Yeah. All right, I want to take a look also at number 11, which is related to this idea. And in number 11, we have an electron with a kinetic energy of, and here we have a very interesting unit right here, 750 electron volts. What does that even mean? Well, if I go back to the idea that delta U is equal to Q delta V, you can see that if my charge happens to be an electron, and the delta V happens to be 1 volt, then 1 electron times 1 volt is going to be a unit of energy. And we're going to call that unit of energy, because we're really imaginative, an electron volt. How much energy is that in joules? Well, it's not too hard to figure, because a volt is a joule per coulomb. And 1 electron has how much charge?
Negative 1.602 times 10 to the negative 19.
Coulombs, that's right. And so when I cancel this, I find out that 1 electron volt is equal to exactly 1.602 times 10 to the negative 19 joules. It's a basic unit of energy for really small particles. So here my electron has a kinetic energy of 750 electron volts, and they want to know now what is its speed. What is the speed of the electron? Okay, well, we know how to do this, because kinetic energy is equal to what basic formula?
And I put in I squared.
1/2 mv squared, exactly so. And it's also equal to 750 electron volts, which I can convert to joules. And I can look up the mass of the electron. Anybody know off the top of the head? Used to. 9.11 times 10 to the minus 31st kilograms. Equals this. And now it's a simple matter to solve for V. Now here's a great mystery. When I multiply these together, I'm going to get a horrendously small number on the right-hand side. See? 750 times 1.602 times 10 to the minus 19th. See? Very small number. But when I multiply by 2, and then when I divide by the mass of the electron, which is very much smaller, I get a humongously large number. So that when I take the square root, I get 1.6 times 10 to the 6 to 7. Meters per second, which is pretty blinking fast. What's the fastest that an electron could possibly go?
Like,
Speed of light. And the speed of light is? No, 3 something. Specifically, 3 times 10 to the 8 meters per second. You can see that we're bumping up against that. This is about 5% of light speed. And this is actually very routine. We don't have them anymore, but have you ever had in your household an old style CRT television?
yes,
With the tube?
those were so cool.
Those were so cool, yeah. In them, the way they function is with beams of electrons that are accelerated by voltage. And the voltage is about 20,000 volts. So the electrons inside the cathode ray tube have a kinetic energy of 20,000 kiloelectron volts, which means that they reach speeds that are something like, I think it's like 20%, maybe 15% of the speed of light.
Is that what we don't have those in our houses anymore?
No, we don't have them because they're big, bulky, and they break.
Wait, what?
Just sound good, that's it.
Yeah, no, actually they're fine. Now, what's unsafe about it is the voltage. So there were big signs on them saying, "Do not service this yourself," and that was serious. If you took off the back and touched it without grounding it first, you could actually kill yourself.
Yeah, my dad actually told this story about how he like serviced a TV once and like the voltage like flew him back across the room.
Yeah. Yeah.
Why does the electricity hurt?
20,000 volts.
Yeah.
It's like,
Well, because it stores up a lot of energy. Is one way to put it. I am in 204 almost all day, except for fourth period I'm in robotics. Thank you.
So wait, what? Okay, I understand the 1/2 mv squared, but then you have like the 750 and all that.
Yeah. We're told by the problem that the kinetic energy is 750 electron volts.
Winter sports
And we
uniforms
simply
are
convert
due
that into
today to
joules.
Mr.
This is
Bennett.
wrong.
I'm sorry.
See?
Winter sports uniforms are due to Mr. Bennett by Thursday of this week.
Joules for
Winter
electricity.
sports uniforms are due to Mr. Bennett by Thursday and at 8. Thank you.
But
Do we actually do that?
I did on the calculator, whatever that turned out to be. I'm going to put onto Edline a solution to problem number 22 because it's a useful problem and it gives us some insight. In the other class, we ended up working different problems from these. And so I encourage you to take a look at the video from the other class as well.
I subscribe.